Hello everyone, it's Marcus Hutchins aka Malware Tech, and today I'm going to be walking through TryHackMe's Advent of Cyber Day 21, aka Help Me, I'm Reverse Engineering. Now this is a reverse engineering challenge, and if you're not familiar with TryHackMe's Advent of Cyber, this is a thing they run every December that goes from the 1st until Christmas Day, and they release a new cybersecurity challenge on every single day. Now, with it being free to sign up and over $100,000 worth of prizes to be won, it is a no-brainer. So we're going to be walking through the challenge today. I'm going to do a little bit of an introduction to reverse engineering, which you can skip if you already understand reverse engineering, though I recommend you don't because you might learn something here. And on the flip side, if you've never done any reverse engineering at all, some of this might sound a bit complicated or overwhelming, but I promise you the challenge is super easy, so just bear with me. So let's get into the story. McSkitty's alert dashboard lit up with an unusual alert. A file-sharing web application built by Glitch had triggered a security warning. Glitch had been working hard during this season's SOCMAS after the last scare with the Yulog exploit, but this alert caused McSkitty to question his intentions. McSkitty began to investigate. It seemed like the source of this alert came from a binary file that had made its way onto the web app's back end. It did not belong there and had some anomalous activity. The binary was compiled with .NET. This whole setup seemed quite unusual, and with Glitch working on the latest security updates, McSkitty was filled with suspicion. As McSkitty continued her investigation, Glitch rushed into the room. "I swear I did not put that there. I was testing defenses, but I wouldn't go that far." McSkitty reassured him, "This doesn't look like your work. Let's get to the bottom of this, put on your decompiling hat, and let's see what we are dealing with." So this is a decompiling based reverse engineering challenge. So there's a couple of ways to do TryHackMe. The first way is you can use the in-browser virtual machine. If you just scroll down and click Start Attack Box or Start VM, you can actually get a split screen view with the virtual machine that's completely usable just from your web browser. Now, the other option is if you install their VPN, you can just remote desktop directly into the machine. Now, this is what I prefer to do because it means it's a lot easier to copy files between my system and the machine, or the machine and my system. So I'm going to be showing you how to do the remote desktop version. So first up, we want to click Access Machines. Then we're going to go to OpenVPN Advanced. We're going to go to Windows because we use Windows. And then we're going to download the OpenVPN config pack, and then download the OpenVPN GUI application. Our system is AMD64, and then we're just going to install those, and then we're going to import the config, and I'm going to show you how to do all of that. So once we have OpenVPN installed, we're just going to go to the OpenVPN icon, and then we can go import file, and then we import our OpenVPN configuration. And once the configuration is imported, we just go back to the OpenVPN icon and then click connect. Now, next up, we need to actually start the virtual machine. So if we scroll down from the challenge, we should actually see a start machine button. And then we'll also have the remote desktop credentials, which is going to show us the machine IP once we've actually started the machine. So if we hit start machine, it's going to take a little while, and it is by default going to open it in split screen mode. So I'm actually going to show you what the browser-based version looks like as well, but we're actually going to use the remote desktop mode, so we'll be closing this as soon as it's done loading. Okay, so now as you can see, the virtual machine is started in this split screen mode. So we could use the virtual machine from the split screen, but I'm actually going to show you how to use the remote desktop version. We can just go ahead and copy this into remote desktop. And then we just want to grab the password as well. Actually, I'm going to copy the administrator name as well because it's too long. We don't want to type all that. It's too many letters. They could have just used admin. And then finally the password, and we should be good to go. Now, it is going to log out the virtual machine in the split screen mode, so you cannot use both at the same time. As you can see, it's logged it out, but we can now close the split screen mode, and then we'll just scroll back to our question section. Now, let's get into the basics of some reverse engineering. One of the first things you'll probably hear about in reverse engineering is the disassembler. Now, it doesn't matter what your favorite programming language is, be it assembly, C, Python, Java, Golang. They're all the same in the sense that the CPU doesn't understand them. The CPU does not understand any programming languages. It speaks purely in binary, or more specifically, machine code. Now, machine code consists of CPU instructions encoded in binary. Now, assembly and machine code has a one-to-one map, which basically means every assembly instruction equals a machine code instruction, and every machine code instruction is an assembly instruction. In fact, assembly is really just the text representation of machine code. It is machine code in its human readable format, because it would be kind of confusing to actually read it in binary. It would also be overwhelmingly long, so it's been simplified to assembler instructions. As you can see here, we have the reset instruction, which simply just restarts the computer, and it's a machine code equivalent. Now, with it being a one-to-one map, that means when we compile assembler to machine code, also known as assembling, we get the equivalent amount of assembler instructions in machine code, and that also means we can easily do the reverse. We have the disassembler, which takes those machine code instructions and converts them back into assembly. Now, that's super easy to do since it's a one-to-one map. Now, one of the other things you might hear about in reverse engineering is the decompiler. Now, decompiling is a little bit more confusing, because when you're writing a language such as C or C++, things can go one of two ways. The compiler can optimize a lot of lines of C code into a single assembler instruction, or the other way around, a single line of C could be a lot of assembler instructions. It could be as many as hundreds or even thousands. So there is no one-to-one map. Now, since the same C code could compile to different assembler code depending on the compiler, or in rare cases, different code could compile to the same assembler code, there is some information loss when we compile C to assembly, and as such, there is no way to turn assembly code back into C. We can easily turn machine code into assembly and assembly into machine code, but when it comes to decompiling, we're actually just guessing. The compiler is just guessing what the C that made this assembly might look like, because we actually don't know. So to give you guys a bit of an example on the difference between disassembling and decompiling, we're going to look at an application I wrote in C. Now, this challenge is .NET, but it's kind of important to understand a bit about C. So this application is super simple. It just calls a function named displayMessageBox, and in the displayMessageBox function, we have a message box call, which is going to create a message box with the title of Hello World and the body of Merry Christmas Everyone. So that's super simple, and then it's followed up by a loop, which will just loop 10 times, and call sleep 10, which will just sleep for 10 milliseconds. So super simple. It does have an icon of a gift box, which I wish I could say was my idea, but it actually just turns out to be the default Visual Studio icon, which would be kind of annoying at any other time of year, but since it's Christmas, it's actually perfect. So we're just going to go ahead and run this, and as you can see, it spawns a simple message box and says Merry Christmas everyone. So now we're going to take a look at it in IDA, and I'm going to show you the difference between a disassembler and a decompiler. So here's what our application looks like in a disassembler. So this is the actual assembly code for the C code that we wrote. As you can see, it's actually quite long-winded, and that's because we have to do everything manually with assembly. So it's setting up the parameters of the call to the message box function, which involves copying the string hello world, Merry Christmas everyone, and then calling message box once all of the parameters are set up. And then if we scroll down a bit more, we can actually see the for loop, which we had in our C code. So this code here, which is basically just 3 lines of C, is all of this assembly code. And likewise, all of this code here, which is maybe 10, 20 lines, is just to do this. Now, as you can see, it is super long-winded, which is why a lot of reverse engineers love decompilers. Now, as I said, the decompiler cannot decompile the assembly code back to the original C. It's just making a best guess about what the C code might have looked like based on the assembly code. So if we just open up the pseudocode, which is basically going to create a C-like representation of the program, we have something a lot closer to the original. So if we just put this side by side, as you can see, it is pretty close, right? We've got our call to message box. We've got our loop with the sleep 10. In this case, it's put it as hex and the same. Now, as you can see, a lot of stuff wasn't recovered because it can't recover it. So at the end of the message box call where we actually set the options, we are ORing the value MB icon information and MB OK. Now an OR operation is like an add, so we're basically adding these values together, which is just going to result in whatever the addition is, which we can actually see here is OX40. Now we just get the value OX40 because we don't know what numbers could possibly have been added together to equal OX40. Like there are infinite numbers in the universe that could be, or infinite combinations of equations that could result in that value. So we can't actually figure out what values were actually set, but we can actually in this case assume them because there are only so many valid values for the message box string. So if we know the value of all of the possible options, we could actually figure out what options were added together to get this value. But as I said, information is lost. But we do have a much easier to read representation here. So a lot of reverse engineers, myself included, would much rather work with decompilers than disassemblers because it is just simply a lot faster. We can very, very easily see what the code is doing here versus our disassembly, which is pretty long-winded. Now, you'll notice it actually it does do a copy here, which we don't have in our code. I don't know why it's assumed that, but the code is close enough that we can see that this is a very simple message box application with a loop that just calls sleep. Now, as I said, machine code runs directly on the CPU, but when we write an application, it isn't just pure machine code. We actually have an executable file format. Most operating systems have them. On Windows, it's the PE format or portable executable, and on Linux, it's the ELF format or executable and linkable format. Okay, so one of the very important things to understand about the portable executable format is everything is compiled into sections, and we need to have a bit of an understanding of what those section names mean. So if I just go into our view and we open up the section view, or segment in this case, we can see all of the different sections within the portable executable. Now we have one called text. Now you might assume that that would contain text, but in any normal circumstance, there should be exactly 0 text in that section. And that's because it's actually the code section. The .text section is the code section. So that's all of our executable code. So if we click on the text section, it just takes us straight to the start of that section. As you can see, start the text section, we have I believe this is the output message box function. So if we scroll down, we'll see after that the start function, and that's the end of the section. So all of our code goes in the text section. In fact, the text section should only be code. No text unless you're calling code text. Now, the text section will almost always be read-only because the code should not be being modified during execution. And if we go to our next section, we have iData, which is the import section. So any functions that we need to call that aren't present in our application, let's say system functions, we're going to import those. So if we look at iData, there should be exactly 2 functions. We have the sleep function and the message box function. Now, both of these are Windows functions, so they're not actually included in our code. The application needs to import them from the Windows libraries and then call them that way. Now, next up we have our RData section. Now, the name here is actually correct in that it does contain data, but since data means basically anything, that's going to be correct no matter what is stored in that section. Now, what the RData section actually stores is application variables, specifically read-only variables, since the R in our data stands for read-only. So it's read-only data. Now, our application had 2 variables. It had the Hello World string and the Merry Christmas Everyone string. So if we go to our RData section, we should see both of those. And as you can see, we do. We have Hello World and Merry Christmas, everyone. Now, if these strings were in any way modified by the code, they couldn't go in the RData section because the RData section is mapped into memory as read-only, which means it cannot be modified and nothing in that section can be modified. So if we were modifying those variables, they would instead be put in a section named data. So we would have an extra section in our application named .data, and that would be for any data that is writable because the data section is mapped as read and write. So any variables that are modified during execution will go in the .data section, and any variables that are static and therefore not modified during execution will go in our data. So it's pretty simple. One is read-only, the other isn't. Now, the pdata section typically contains stuff such as exception information, but we're not going to get into how exception handling works, so we're just going to skip over that one. And lastly, we have the RSRC, which is short for resource. The resource section is for us to store really whatever we want. Maybe we have something that isn't necessarily a variable or a static variable. Maybe it's some other data that our application uses. We might put that in the resource section. In this case, we actually only have one thing in the resource section, which we can't read because it's actually a PNG file. It is the application icon. So the application icon is stored in the resource. So this is actually going to contain the bytes of our application icon. So we're actually going to have a bit of a look at the PE format because this is a Windows application. So it's going to be in the PE portable executable format. And a very nice application for doing that is PE Studio. So we're just going to go ahead and drop the demo application into PE Studio. So what PE Studio does is it parses the portable executable format and it outputs all the various values and settings in a very human readable format. So as you can see, we can see a lot about the portable executable. We can see it was built for AMD 64, so a 64-bit machine. We can get the PE file signature. And we can actually see if we go to the optional header, we can see a bunch of different things such as the entry point, the size of the code section, the size of the data section. So it's super useful. It has a lot of very interesting information. Now, one pretty useful setting here is the indicator setting, which actually tells us this is a Microsoft .NET application, which means if we were to open it in a native code reverse engineering tool such as ILA Pro, it's probably going to get very, very confused because .NET is not compiled to native code. Now, .NET code is a little bit weird. Remember when I said machine code runs directly on the CPU and C is compiled to assembly, which is assembled to machine code. So C code is compiled to something that runs directly on the CPU. Well, .NET isn't. .NET actually compiles to IL or intermediate language, which is a kind of bytecode that doesn't work on the CPU at all. The IL code is basically interpreted by the .NET framework. So the .NET framework works as a sort of virtual machine, which takes that IL code and then it translates it into machine code. And you're probably thinking, well, why would you do that? Like, why would you compile your code to another code, which then has to be compiled to machine code anyway in order to run? Now, one of the very common and very simple reasons for it is portability, because as long as we put the .NET framework on a machine, it can run IL code. So it doesn't matter if our machine is an Intel CPU, an AMD CPU, an ARM CPU, if it's 32-bit, 64-bit, as long as that machine has the .NET framework running, we can run the same executable on any machine, which is something you can't do with native code like C or assembly. When we build an executable in C or assembly, it has to be compiled for the specific architecture on the specific operating system that we want to run. So if we want to run our application on Windows 32-bit, we need to compile a Windows 32-bit application. If we want to run it on 64-bit, we have to compile a 64-bit application. If we want it to run it on Windows ARM, we have to compile a Windows ARM application. And that becomes a lot of applications, especially if we're working with Windows, Linux, and Mac and mobile. We end up just making more and more different versions of the same application. Whereas with .NET, we can just make a single .NET binary, and then as long as all of those systems have the .NET framework installed, that same binary will run on every system. Now, this sounds very, very complex, but this actually has a very, very strong benefit. Now, one of the really big benefits with IL is it's actually closer to the original code than machine code is to C. So when we compile C, we actually lose a lot of information, which is why I said the decompiler is only just giving us a best guess what the code might have looked like. But IL code contains a lot more of the original information from the original code, which means we can actually decompile IL code to a much closer representation of the original code than we could with native code. So that's why .NET is actually really easy to reverse. Now, because .NET isn't native code and doesn't compile to machine code, we can't use traditional reverse engineering tools. But we can use something called ILSpy, which basically allows us to decompile IL code. So what we're going to do is we're going to open up ILSpy, and then I'm just going to show you with the demo application first, and then we're going to reverse the actual challenge. Okay, so now that we have our demo binary open in ILSpy, I'll show you how easy it is to reverse .NET. So we're just going to open the dropdown, we're going to go to demo binary and then the main function, and here is the entry point. So this is the first code that would be run when the .NET application is executed. Now the first thing it does is console.writeLine. Now if we didn't know what this meant or what this does, we could simply look it up on MSDN and it will explain to us. It writes the specific data followed by the current line terminator to the standard output stream. That's a very long way of saying it writes it to std out, which in most cases is going to be the system console. So this is a console application. So it's going to write hello thm demo binary. Now the next thing it's going to call is thread.sleep, which sleeps for a certain number of milliseconds. In this case, we've got 5,000, which is 5 seconds. So it's going to wait for 5 seconds. Now it's setting up a string named address with this, what looks like a web URL. So we're just going to copy this. Next, it's getting the environment folder path, which is the special folder.desktop. So it's getting the path to the system desktop. And then it's combining it with the name thm-demo.png. So it's basically generating the path for thm-demo.png on the desktop. Now we're creating a new web client, and then we're doing another console.writeLine, this time writing downloading file ... Then we're calling webclient.download with our original address. So it's going to download this file right here, and then it's going to save it to this path right here. As you can see, address, the first parameter is the URL, and the second is the destination path. So it's basically going to download whatever is at this URL to a file on the desktop that's named thm-demo.png. And then it's going to call process.start, which allows us to launch a new process. Now, in this case, because it's a PNG, it's not going to launch any kind of executable. It's just going to open up the PNG in most likely whatever our default image viewer is. We have, and then finally, it's just going to output image open successfully. Bye-bye leaving demo binary, and then it's going to sleep for 5 seconds and then most likely exit. So if we run the demo binary, we're going to see that we should get a PNG file on the desktop. So it's going to sleep for 5 seconds, 3, 4, 5, downloading file downloaded, and then it's opened it up in our default image viewer, which is photo viewer, and it's a very nice image. So for this challenge, we need to reverse engineer the Whereville app. Now, fun fact, where is actually short for malware. It's not, but it might as well be, because a lot of wares are actually infected with malware. probably one of the most ironic ones that I ever saw was a cracked version of IDA Pro, which was infected with North Korean malware. Now, since IDA Pro is a tool which is very popular for reverse engineering malware, it would be quite funny that a malware reversing tool would itself be infected with malware. But no one actually noticed because you typically don't reverse engineer your reverse engineering tools, so it actually went unnoticed for quite a few years. But anyway, back to the challenge at hand. So our first question is, what is the function name that downloads and executes files in where_villapp.exe? So there's going to be a function somewhere that is downloading and executing something, and we need to find out what it's called. So again, we're just going to open up ILSpy, and this time we're going to drop in our where_villapp. Okay, so we have our where_villapp open in ILSpy, and we're going to do the same thing. We're just going to go to the where_villapp, and then we're just going to go to, this one is called Fancy App, so we're going to go to Fancy App, Program, and then Main. So this is our main function. Now, in this case, it's just running a form. So we have a form named form1. So we're going to have to find form1 in the dropdowns, which is right here. So here we have form1. We're just going to expand everything. We have a function called initialize component. So here we have a function called isWindows, and it checks if it's not Windows. And if it's not Windows, it says the application is only compatible with Windows. It cannot be executed on this operating system, and then it exits. So as I said earlier, .NET applications, because they use this intermediate language, they can run on any architecture and any system. So in this case, the application itself has decided it's only going to run on Windows. Then it sets timer1.interval to 3000 and calls timer1.start. So we have our isWindows check, we have our timer1.tick check. Okay, so here we go. Timer1.tick is going to be called when the timer ticks, and it's going to tick at a specific period. Now, as you can see, we set timer1.interval to 3000, which I assume is milliseconds, so that is 3 seconds. So after 3 seconds, timer1.tick is going to be called. It's going to stop the timer. It's going to, I guess, hide the executable window, and then it's going to call this download and execute file. So we can assume that is the download and execute file function. So we're just going to put in the function name. And that should give us the correct answer. Perfect. So the next question is, once you execute where_villapp.exe, it downloads another binary to the download folder. What is the name of the binary? Now, when it does say once you execute, but given that we're reverse engineering malware, it's not real malware, but in a real world scenario, we would not want to execute that. We don't want to be running malware on our system. So one way to answer this question would be to just simply execute the application and see what shows up in the downloads folder. But we're going to do this the malware analyst way and not run the application, which is known as static analysis. You have two types of analysis: static analysis, which means just reverse engineering and looking at the code. And then you have dynamic analysis, which means running the executable and maybe stepping through it in the debugger or using some kind of sandbox software to get information about the application as it's running. But we're not going to be doing that today. We're going to be doing purely static analysis so that you can get an idea of how you would actually do this in the real world. Okay, so now we're just going to decompile the download and execute function and then try and find out what it's actually downloading. So as you can see, it's very similar code to the demo application we used. It's setting a string named address and a second string named text. This time it looks like it's getting the download folder. Yep. So it's going to download a file into the downloads folder named explorer.exe. So that is our answer. In fact, it's actually already named explorer.exe, but it's making sure we're definitely going to write it to a file named explorer.exe. So the answer is clearly explorer.exe. So we're going to go back to our questions and just type that in. And again, we've got the correct answer. So our next question is, what domain name is the one from where the file is downloaded after running where_villapp.exe? Again, we're not going to be running the app because we probably wouldn't want to do that. So we're going to just copy this from here. So it's mayorc2.thm. And again, correct answer. Okay, so next question. The stage 2 binary is executed automatically and creates a zip file comprising the victim's computer data. What is the name of the zip file? So in order to answer that question, we're actually going to need to get the downloaded second stage executable. Now, this is actually something we would see in a lot of real-world malware. It's pretty common for malware to have multiple stages. The actual malware would not be the first thing to land on the victim system. It might start off with something like a doc file or a zip file, or even an ISO file, a JS or WScript file, and that file would then download and execute something else. And in a lot of cases, that would be a loader, which would be responsible for downloading and executing the final piece of malware. So you would start off with your initial entry, which would download and execute a loader, and then the loader would run, and then that would download and execute some malware, and then the malware would run. So you typically have 3 or more stages in a normal malware infection chain. In this case, it looks like we might have 2, but we need to go and get that second stage binary. So we're just going to manually download it because, again, as I said, we don't want to be running malware on our system. We are in a VM, so we could if we really wanted to, but it's best to avoid it if you can. So I'm just going to copy the domain name, and then we're going to open it up in a web browser. So as you can see, we've downloaded the second stage binary, and now we can begin analyzing that. So we're going to do the same thing again and just drop the explorer.exe binary directly into ILview, and it's most likely .NET as well. So now that we have the explorer.exe binary open in ILview, we can see that it is also .NET. It's called file collector. And then if we go again to the main entry point. So in a lot of programming languages, the entry point is simply called main. In C, it's called main or winmain for Windows applications. In Python, it's called main. So oftentimes you can just skip straight to the function named main. In C#, it is again called main, except it begins with a capital letter. So we're going to just look through the code. So it's creating an array of file names. We have docx, PowerPoint, PNG, GIF, and JPEG. Now it's getting a folder path, and this time the folder path is called My Pictures. So it's going to log searching for files in folder path. So it's going to look for files in My Pictures. Now, since it's already created an array of file extensions, we can probably assume that that is the file types it's looking for, but we won't go with that until we've actually read the code a bit more. So next up, we've got path.combine collected files. So it's creating a subdirectory named collected files in get temp path. So it's getting the temp path, and then it's appending the path name collected files and then calling create directory. So all this is going to do is create a directory named collected files in the temp folder. So temporary folder created, and it's going to output the name of that directory. So next up, it's going to call directory.getFiles on that first folder path we created, which is the My Pictures folder. So it's going to search every file in the My Pictures folder and every subdirectory by the looks of things, and then it's going to iterate each file that it finds. Now here we've got the sources.ne, which, if you remember, we created an array of file extensions. This is basically going to say if the file ends with any of those extensions that we searched for, then we're going to, by looks of things, copy it. And then finally, we're going to create a new path again in the temp path, and we're going to create a file named collectedfiles.zip. And then it looks like we're going to use the zip file.create from directory to basically just zip up that entire directory. So in short, we're basically just going to get any doc, PowerPoint, PNG, GIF, or JPEG files from the My Pictures folder or any subfolder. We're going to copy them to the temp directory under a folder named collected files, and then we're going to zip the folder named collected files to a file named collectedfiles.zip. So there we have another answer. It asked us what is the file name that the files get put into, and that is collectedfiles.zip. So that should be the answer to the next of our questions. Okay, so again, correct answer. And it looks like we have one final question. What is the name of the C2 server where the stage 2 binary tries to upload files? So that's already telling us what this application does. It's already kind of told us that it steals files, and it's telling us that it's uploading them somewhere. So we just need to look at the next part of the code. So it looks like it first copies the zip file to the pictures directory for some reason, and then it calls the upload files to server function. So here you can see it calls web client.upload, and it uploads address from zip file path. And here is our address. So that is the C2 that the files are going to get uploaded to. You can see it sets the address, and then it calls the upload files function with that address. So anonymous c2.thm is the answer to that question. And there we go. So I hope that walkthrough helped you out, and if it did, please hit like and subscribe because that helps me out, and I will be back with some more videos soon. Merry Christmas and a Happy New Year.